Hello everyone, today we're going to be talking about derivatives, and this is part of the San Antonio Math Include 9th grade calculus class for the year 2020 to 2021. For those of you who are just wandering through San Antonio Math Include's channel and you're just seeing this video, that's what this is part of. I was unable to hold the actual virtual Zoom meeting that we were supposed to have, so sorry about that, but this should be just as helpful. Today we're going to be talking about derivatives, and when you first are introduced to calculus, it's basically just derivatives and integrals. So calculus, or derivatives in calculus, are so important, and it's really important to understand what they are. But because there are so many different ways that derivatives are used in calculus, it's going to be really difficult for me to try to show you all those different ways that you can see derivatives show up in a problem, which is why I'm not going to be talking so much about the different types of practice problems you would see or types of problems you might see on an exam. And I'm going to be talking more about what a derivative is as a concept and how it can be applied, because I think that's more important for you to understand what a derivative is, and then you'll actually be able to use it in your tests or your classes. So there are many different equations you're going to have to memorize in terms of derivatives. Like, for example, there's something that you just have to memorize is that the derivative of cosine is negative sine, and I will show you different cheat sheets of like formulas that you have to memorize, but I'm not going to go through all of them with you today. So let's go ahead and talk about what is a derivative. So a derivative, it just shows you the slope of the tangent line at a specific point on a function. So then what is a tangent line? A tangent line is literally just a line that touches a function at some point, and it has the same slope as that point. So it's a tangent line touches a function at some point, and at that point it has the same slope as that one point. So for example, let's look at this curve. This curve has a different slope depending on which point you choose. Like, for example, I'll do this in a different color. At this point right here, you have like a slope that maybe is about something like this. I don't have any units here, so I can't actually tell you what it actually is, but it'd be something like this. A line that has the same slope might be similar to that one. Whereas right here, the slope is more flat. So it might be something like this. These are both the tangents. Both of these lines that touch the function at some point and then take on that point slope, those are tangents. So here's another example. Right here with this first line I have pre-drawn, the slope or the curve is something like this, and then at this point we have a slope or a tangent line that would take on a slope approximately equal to this, and so the line might look something like that. The tangent might look something like that. And another tangent line we might see is like at the bottom of this curve, when it's starting to increase more, but it's still not exactly a high slope. It's kind of low, so it's almost sort of relatively flat. And this last green line here, this other tangent line, as you can see, the graph becomes much more steep and sloped. And so if we choose a point here and make a line based off of the slope at that point, we're going to get a tangent line similar to this green one here. So I hope that sort of clarifies what a tangent line actually is. So now we can go back really quickly to the definition of a derivative. A derivative is basically just the slope of that tangent line. So if I take the derivative at this point right here, it would just be the slope. So literally just taking the derivative will show you the slope. But it's not as simple as that because there are different ways that you can use derivatives. However, if you're given a graph and you're asked to find the derivative at, say, some point x equals 3, then you would literally just find the slope at x equals 3. So I hope that sort of clarifies any confusion on that, but there are different applications of a derivative, and there are actually many applications. So some of the ways that you might see a derivative used in calculus include rates of change. And so, for example, this might be like, I've seen so many problems that are like something being added. Say, for example, dirt is being added into a container, and they want to find the rate of change of the volume of the dirt in that container. That rate of change is the derivative. So you would have like some equation, and then you take the derivative of that equation. But that's essentially how derivatives would be used for rates of change. Also, they're used in maximums, minimums, and points of it. Oh, that says interception. That is actually points of inflection, which we might also abbreviate as POIs. So these are all critical points, which we'll talk about later, but essentially like whenever you see a maybe a parabola, this would be the minimum, and we can find the minimum by taking the equation of the parabola, let's say it's just x squared, and then finding the derivative. And we'll talk more about what this is, but this essentially means find the derivative. But yeah, like I said, we'll talk about that one a little bit more. Also, you'll see them in Taylor and Maclaurin series, which you actually don't have to know until Calculus BC. That's what this is, Calc BC. But yeah, there are so many derivatives in series, which are not my favorite topic, but they're basically half of Calculus BC. Also, integrals, you might remember I said that when you're first introduced to calculus, it's just integrals and derivatives. And in some ways, integrals are literally just the antiderivative. So it's just the opposite of a derivative. So we'll talk about it later, but if you've already been exposed to what a derivative is, then you would know that, say, for example, if you take the derivative of x cubed, you get 3x squared. But if you were to go backwards and you had the integral of 3x squared, then you would get x cubed. So don't worry about this if you have no idea what I'm talking about. It's just sort of, for those of you who have already been exposed to what a derivative is, this might help you process it. The derivative of x cubed is just the integral of 3x squared. You'll also see derivatives used in optimization problems, which I also don't like, or at least I didn't like them at first. Now they're not too bad because I understand them, but it's like, essentially, one typical problem you might see is that you have a certain amount of fence and you want to use different lengths of wood to optimize the area of your fence. Yeah, kind of boring stuff, but it's actually very applicable to life because, I mean, it's also dealing with salaries too and paychecks. You want to figure out the maximum pay that you need for such and such, whatever you want to buy, or like rent or something, and you need to figure out how you can best optimize that and basically how much you have to work. Also, if you like physics, a lot of physics deals with derivatives and graphs. So a lot of physics deals with calculus. If you don't like physics, don't be dismayed. You actually don't have to know physics for calculus. But if you go into higher level physics courses, I believe it's not required that you know, but it's certainly very useful. Like, I've used calculus for physics, so that's certainly very useful, especially with graphs such as like position versus time or velocity versus time, that sort of stuff, which I can talk about more if we have time at the ends, because I want to keep this to like about 40 minutes. But most of calculus, like I've already said, is either derivatives or integrals, so there's a lot to cover. So brace yourself. We're going to talk about how derivatives are expressed and what their notation is. So here are some symbols for a derivative. There's f prime of x, which is this. It's literally just f prime of x. That's how you would say it. And this denotes the derivative. So if you have f prime of x equals something, that something is a derivative. Another way to indicate what a derivative is if you use dy over dx. These are the same thing, just in different forms. Also, remember that f of x is like a function. This means the function that they're referring to. This can also be used as like f of x equals, let's say, x squared. In this case, f of x is y. So f of x is y / the function. But remember that you can also have different symbols to denote the function and what y is. You can have like g of x, which you'll see, or h of x. These are all equal to each other. But you might also see something like, I don't know, g of z, where g of z is the same thing as f of x, just using different variables. So all in all, if you see something like, take d over dx, which we'll talk about here in a minute, if the function is g of z, then you would have d over dz. So just don't be confused if you see different variables in what looks like it would be a familiar equation, because it's the same thing. So speaking of which, if you have d over dx of, say, I'm just making up a problem here, but d over dx of 4x squared, then this is asking you to find the derivative. So you'll often see something like, what is d over dx, and then some function, whereas this is the function. But it'll often ask you like, what is d over dx of something, and so in that case it's asking you to find the derivative. Just don't be confused by that. So even sometimes, like, I've seen in problems and I've gotten confused where it's talking about d over dx of something and it wants me to find the derivative, but it doesn't explicitly say find the derivative. So just don't be confused by that. But also, we'll talk about this last one here more when we get to critical points, which I already mentioned, and especially concavity. For those of you who don't know what concavity is, really briefly, we have a parabola here, and this would be concave up, and this one would be concave down. Essentially, it's just which way it's facing, although there's a more calculus-based explanation, but I won't get into that so I don't confuse you. Essentially, this is the double derivative. Both of these are. So if you ever see f double prime or the second derivative of something, it may look something like this and then have a function after it, but that essentially just means that you take the derivative twice. So you have one derivative, say it's like x cubed, and then you take the derivative once, and you get 3x squared, and then if you take the derivative again, you would get 6x. So this is f double prime of x, and this is f prime of x. So these are all different symbols that you have to remember, but for now, the most important ones that you have to remember for a basic understanding of calculus, or not for a basic understanding of calculus, but for a basic understanding of a derivative, you would have to know this right here and this one. You may have to know about this one, but we can talk about that later, and it's sort of more self-explanatory once we get to integrals. But for now, mostly just these two you'll have to memorize. It's not that bad, though. So there are many different ways for a problem to ask you to find the derivative of something without actually saying the word derivative. So for example, as we've already talked about, you might see a problem ask you to find the rate of something, like the rate at which the volume of dirt in a bin is changing. So you're going to need to find the derivative because the derivative is that rate of change. Now, in other instances, you might have to take the second derivative or the third derivative or something like that. And you're still having to take the derivative, but you might have to take the derivative multiple times. It just depends on the problem and the wording of the problem. Another instance in which you might have to find the derivative is when you're asked for the slope. So, for example, let's just draw a random graph and say that this is f of x equals x squared. And just remember, this is the function. This essentially just means the function in terms of s. So I have actually seen before, like, f of y, and that would literally mean the function in terms of y. So instead of this being, like, f of y, you don't really have to know this. I'm just trying to, like, drill this point into your head for what this is, what this means. It would be the square root of y, because in this case, y equals x squared. So if we want to put things in terms of y, then you would take the square root of both sides and you would end up with the square root of y. So that was a little bit of a tangent. Sorry for that pun, but like, this is something that's important to know. However, it's not really for this problem. So, like I said, if we have this function, and this function is f of x equals x squared, let's say we have the point 0, 0, and we also have 2, 4. Because if you plug 2 in for x, then you get y equals 4. So let's say that you want to find the slope of the point 2, 4. Well, you can't just, it's not a line, so it's not like you can just use the m value or whatever it is for y equals mx plus b, because for a line the slope is always the same. So the tangent is literally just the same along the line. It's literally just the same line because it's the same slope. But here we have different tangents at different points because the slope is different in different places. So if we were to find the slope at the point 2, 4, then that's really asking you to find the derivative at the point 2, 4. So if I were to find the derivative at this point, just to like show you, I know we haven't really talked about finding the actual derivative yet, but if you do want to know, it would just be taking the derivative, which is 2x, and then plugging 2 in for x because we're using this point. So it would be 2 times 2, which is 4. So the slope would actually be 4. Also, if you hear really like heavy, unnatural breathing in the background, that's my dog. Don't be alarmed. She's a big dog. But anyways, this is very similar to find the derivative, but differentiate. You'll see like the same sort of root in there. It's essentially find the derivative. Actually, it's literally find the derivative, so don't be confused by that. Also, once again, d over dx, like we talked before, it literally means the derivative with respect to s. So like I said, if you have a function that's like f of g, then the notation would be d over d of g, where g is actually s, but we're just using a different variable to represent that. So we're not really going to talk about this one too much. You don't really have to know that until a little bit later. But just in case you have been exposed to this in class and you're confused about what it is, that should sort of cover it. Oh yeah, and there are multiple different formulas for finding the derivative. This is why I have formulas in quotations, because there are so many different ways to find the derivative, and you will not be able to use the same formula for different questions. So, for example, let's just talk about this first formula. It's essentially where, remember that this is just find the derivative. Find the derivative. And that whenever this is given here, it's literally asking you a question. It's like, what is this? So, if we wanted to take the derivative of x of n, which is this function here, then the equation for doing so would be taking that n and multiplying x by that, but then raising x to the power of n minus 1. So you're just taking x to the n and then moving this down here, so it's n times x, but then n becomes n minus 1 in the exponent. So for example, if we were to do this problem right here, x to the power of 3, and we wanted to find the derivative of that, then you would take that 3, move it on down, and then you take 3 minus 1, which is 2, so you end up with 3 times x squared. So just really quickly, another similar problem, we'll just do 2 times x to the 5. So if this is our n, our 5 is our n value, whatever the exponent is, that's your n value, then you would do 2 times 5, because that's n, times x to the 5 minus 1. So you would end up with 10 times x to the power of 4. So I hope that makes some sense. We also have some other problems, or other different formulas. So some other formulas you might have to use include if we literally just have a graph. That's a terrible line, but that's a graph. And we have some like y equals 2x. This is our line, and we wanted to find the slope of some point. Well, let's say we wanted to find the slope of point B, and we have point A, which is the origin. That's point A. And point C is up here. So if we wanted to find the slope here, or if you wanted to find the derivative at point B, the derivative at point B would literally just be the slope, as always, but you can find the derivative in this case by using the slope formula. And the slope formula is, well, there are different ways to write it out, but I usually use y2 minus y1 over x2 minus x1. You could also say change in y over change in x, but whichever way that you say it, this is still the slope formula. So you would just use this slope formula, and that would get you the derivative, because the slope is the same at every single point along the line, because it's the same equation. It's the same line. So yeah, you can also use the slope formula occasionally to find the derivative. There are some other limits. We've talked about limits before, but limits are also important for derivatives. So, for example, the other formula that you need to know, let's say this is formula 1, this is occasionally formula 2. Formula 3, just do it right here, looks something like this. Limits as x goes to a of f of x minus f of a over x minus a. And you'll see this multiple times throughout the year. This is actually one of the most common ways to define a limit, because this is actually just the slope. because f of x minus f of a, these are both y values, but they're different y values. And then x minus a, well, this is like one x point, and this is another x point. They're both constants. And in this case, f of a is still some x value. It's some x value, but this x value is not equal to the actual x value. So these are both x values, but they're not the same. And that's the whole point of using different variables, to show that, like, yeah, f of x and g of a are both functions, but they're both different functions. And so x is an x coordinate and a is an x coordinate, but they're not the same x coordinate. So here, sort of a roundabout way of explaining that this is still like y2 minus y1 over x2 minus x1. But that does not mean that, like, you're still going to definitely have to know this. Several times I've come across questions where I have to use this next formula, and I would get so confused because for some reason I just always forgot about this one. But that's limit as h goes to 0 of f of x plus h minus f of x over h. And there is a way to derive this. You don't necessarily have to memorize. You can derive it and, like, actually be able to figure out mathematically what this equation is. And there are multiple, like, videos that you can look up for how to derive this. Or if you want one, just, like, email me. But I'm not going to explain it here since I'm sort of on a time crunch. However, you still definitely have to know this. Like I said, I've come across problems before where it's like, find the derivative using this. And I'm like, I have absolutely no idea what this is. But essentially, this is equal to f prime of x. So we'll do an example problem with this equation. But yeah, you're definitely going to have to know this. Alright, so also one thing I want to mention, this is called the definition of a derivative. So a problem might literally ask you, use the definition of a derivative to solve this. So just remember that if you see this, it's referring to this here equation. But let's do an example problem. So let's say that we have some f of x, and that function is 3 minus 14x. And so if we wanted to use the definition of the derivative to find the derivative of this function here, then we would say, we would take our equation, we'd say limit as h goes to 0 of f of x plus h minus f of x over h, and we would plug in this formula basically every time where we see f of something. So remember that f of x is the function and x is the variable, the x component. So here, when we have, I'll use a different color here so it doesn't get too confusing. But here, when we have f of x plus h, this is still a function, but now our x variable is x plus h. So this is our whole x variable. So if we wanted to plug in this function here into here, well, we would do 3, I guess I'll go back to the normal color. We would say 3 minus 14, but instead of x, you do x plus h, because you have to adapt this here function into this function, where this previous function is, its x component is just x, and this new component is just x plus h. So now here you have 3 minus 14 times x plus h. But here, in this latter part, it's just, the x component is just s. So you don't have to modify the original function. It's still 3 minus 14 times s. And all over h. And don't forget to write out the limit, as I did here, in front of this problem. Because if you do that on an AP question, even if you skip down a couple lines and then write limit here, but you don't write the limit here, then you wouldn't get the point. So just always remember to do that. But now we can just evaluate this. So to evaluate this, we're basically just going to simplify it. So we have the limit as h goes to 0, 3 minus 14h minus 3 plus 14x all over h. So these cancel out. So we have a positive 14x and a negative 14x. And this also cancels out. We have a positive 3 and a negative 3. So we're left with the limit as h goes to 0 of negative 14h over h. And before you plug in 0 for h, remember you have to simplify this first. So we simplify and our h's cancel out. So see, if you had plugged in 0 for h, you would get negative 14 times 0 divided by 0, which would be indeterminate or undefined, which is wrong because you have to simplify it first. So here we have that our answer is negative 14. So this means that the derivative, or f prime of s, equals negative 14. Another thing that might be useful that I just thought of, for those of you who have taken a physics course, I know I took physics before I took calculus, and not AP physics, I've just taken more standard physics courses. So this one might make sense to you. So we have different graphs, and let's say that this is distance versus time, this is velocity versus time, and this is acceleration versus time. So our distance curve may look something like this. And if we wanted to take the derivative of the distance, well, here's something to think about. The derivative of this graph right here would give you velocity. Because if you took the slope at some point, you would get velocity. Because what is the slope? The slope is y, or change in y, over change in s. And in this case, our y value is our d value, and our x value is our t. So you would get d over t, which is the equation for velocity. So if you take the derivative of the distance versus time graph, you would get the velocity versus time graph. And while this here is a curve, let's say that this is, I know I've used this equation a lot today, but let's just say that our function is y equals x squared. Well, if we wanted to take the derivative of that, then our derivative would be 2s, because remember, it's x to the n becomes n times x to the n minus 1. So if we were to take the derivative, we get 2x, and that might look something like this. It's just a line, but it's an increasing line because it has a positive slope. So if we were to take the derivative of the velocity versus time graph, you might already expect this, but we would get acceleration, because the derivative of the velocity versus time graph, which is change in y over change in s, our change in y is velocity, and our change in s is our t, so our slope, which you may also see as m, like in the y equals mx plus b equation, where m is slope and b is our y-intercept. Just really briefly, if you didn't know that, that's like the standard linear equation. But if you see me write m, that means slope. So here our m is velocity over time, which is the equation for acceleration. And if you haven't been exposed to these sorts of graphs before, remember this is physics. However, you do still have to know actually that if you were to take the derivative of a graph, you would get the rate of change, and if you were to take the derivative of that graph, you get the rate of change. So, for example, I've come across multiple problems, especially in AP FRQs, where they talk about finding the derivatives of something, and you have to interpret that value. And so you might have to say something like the rate of change of x, and it's just a whole mouthful to write out. But either way, something else that's interesting is that velocity, the definition of velocity, if I remember correctly, it's been a while since I've taken physics, is the rate of change of distance, and acceleration is the rate of change of velocity. So plugging in that definition of velocity, acceleration is the rate of change of distance. So, and remember that rate of change is just the derivative. So it's kind of confusing, but hopefully, if you understand that, then you're gonna grasp the derivative concept better. Also, if we were to take the double derivative, or if we were to take the derivative of the derivative, then you would get 2, because, I'll do this down here, but because 2 to the x is essentially 2 to the x to the power of 1. So it'd be 2 times 1 times x to the power of 1 minus 1, which is 0, and anything to the power of 0 is 1. So you would end up with 2. So here, let's say this is 1, that's 2. Our acceleration line, or our acceleration graph, is just a flat line, a horizontal line at y equals 2. So like I said, if you can understand that taking the derivative of the distance versus time graph gives you the velocity, and taking the derivative of velocity gives you acceleration, and how this x squared curve eventually becomes a flat line, then you will have a better grasp of the derivative concept. So I think we have time for a few more problems, but I ran out of pages on this PDF, so I will just make something up. Also, definitely email me if you have any questions. And you guys are all signed up for the class, so you should already have my email. Okay, let's make up a problem here. So let's say, let's just do something simple at first. Okay, let's start with something simple. We'll say something like 3x to the power of 9. So if we wanted to find, the problem may look something like this, and it's asking you to find the derivative of 3x to the power of 9 with respect to x. That's how you would say that. Now, if you, you can just say d over dx of 3x to the power of 9, but just so you understand, because when we get to integrals, you're going to have to have a better idea of what d over dx is. Okay, so this would be 3 times 9, because 9 is our n value, times x to the power of 9 minus 1. So we'd end up with 27 times x to the power of 8. And this is our derivative. Now let's say we have another problem with some graph that line was going to bother me. Some graph with a line like this. And we wanted to, let's say that this, actually we'll make that a little bit longer. This is x equals 5, this is x equals 3, and then we have 0, 0. And we'll say that we have the points 5, 3, and we have the points 0, 0, and 3, 2. So we want to find the derivative of the equation, derivative of the function at x equals 3. And I know I hadn't talked about this part right here, but whenever you have d over dx of some function, you can draw a line, or you may see a line with some x equals and then a value. And this essentially means that you're finding the derivative at this point, at the point where x equals such and such number. So just keep that in mind. So right here, we have the derivative of the function at the point x equals 3. Well, the good thing about this is that it's just a line. So if we were to find the derivative of this function at x equals 3, well, it has the same derivative or the same slope at x equals 1, at 2, and at every single point on this line, because it's just a straight, unchanging, positive sloped line. So we can use the slope equation here. So we'll take the points 5 over 3. You can use any points, but I'm going to use 5 over 3 and the origin points. So we'd have 3 over 5, and that's our slope. Remember, slope can be denoted by m, which means that that's our derivative at the point x equals 3, but also at every other point as well. So I just made up this problem here, and it's more of an actual FRQ style, or free response question styled question. So it's more likely that you're going to see questions more similar to this than just simply like what we had for question 1, just find the derivative of such and such. So here's the question. Pounds of grain are being poured into a silo, and the equation for finding the weight of the grain in the silo at any time is WT equals T to the power of 3 plus 3. What is the rate of change in the weight of the grain with respect to time at time equals 2? So our Q word here, or our Q phrase, is rate of change. Remember that this is derivative. Whenever you see rate, you're going to think derivative. And I can't think of a problem where it actually wouldn't be a derivative. So here, we have to find the derivative at the point t equals 2, because that's when we're finding the rate of change of the weight. So remember that WT is our weight, and t is our time. And if we want to find the derivative, or d over dx, of WT at t equals 2, remember that t is an x component, but like I said before, we have different variables to represent different x components. So here, this is how you would write it out, and then you want to solve it. So you would take the derivative of, or I guess just the derivative would be, so t cubed plus 3 becomes 3t squared. Oh, and I forgot to mention this, but the derivative of a constant is 0. The derivative of a constant is 0. You're going to have to remember that. Like, absolutely 100%, the derivative of a constant is 0. Okay, the derivative of a constant is 0. So here, our 3 value is just gone. So we are left with 3 times t squared. And this is the function that we're going to use. And now that we have our function, we have to find the rate of change in the weight at time t equals 2. So now we plug in 2 for t, and we get 3 times 2 squared. So we get 3 times 4, which is 12. So the rate of change in the weight of the grain with respect to time at time equals 2, and we'll just say it's 2 seconds. It would always tell you, but I forgot to write here because I just randomly came up with this. We would say that the derivative, if we wanted to write it with units, would be 12 pounds per second. So if we wanted to interpret the derivative, and you're going to be asked to interpret a lot of values in calculus, if we wanted to interpret the derivative, it would be the rate of change in the weight of the grain when time is at 2 seconds. So it's already written here in the problem, but just be aware that you might be given a question when it asks you what is d over dx wt at time t equals 2 seconds, and then it's going to ask you to interpret the derivative, and you would say the rate of change in the weight, blah, blah, blah. Okay, I hope this was helpful, but if you have any questions, because I know that there's so much covered here, and I have so little time, just please email me or let me know, and I will get back to you ASAP. But thank you all for those of you who are watching this lecture, and I hope it was helpful if you needed help, and I hope it clarified things.